And then we can start. Right, okay. I'm assuming you can see the screen and hear me on Zoom. Great. So today is about a recap of what we covered in the last 15 lectures. The last 15 lectures, we covered chapter 1 to 10. In today's lecture, I will not talk about new topics. Think about it as a story of what we went through and what you went through. And it's a good way to see if any of these topics are still strange to you and you are uncomfortable with that. So that's a sign that you might want to use office hours or do some self-study and hopefully ask questions about it on Piazza. And we're here to make sure you understand these topics. So it's not intended to going through a lot of details and solving examples. It's more about the story of the first 10 chapters of the book. Okay. Our story started with a system of linear equations. We said in linear algebra, we're motivated to have a system of linear equations and find a solution. And then we wanted to know what are the possible cases that we can face. One of them was that there might be no solution to the system of linear equations. Then we wanted to know that if there's a solution, then if that solution will be unique. Or we could see a case that there are infinite number of solutions. So we started with this motivation, and the reason we could convince ourselves that this is the case was by looking at maybe two equations, two variables, and visualizing them. Because later we scaled them to high-dimensional vector spaces. It was not possible to visualize anymore. So case one, we have a unique solution. You can plot two lines. Basically, we have y equals 4 minus x, and y equals 2x plus 1. Each equation is giving you a line. And then you can define your x and y. You can plot two lines. I used alpha from Mathematica online to visualize it. So you don't have to do it by hand. You can use Mathematica alpha search to solve a lot of math problems. That's how I generated a plot. So in any case, you visualize two lines and you see they intersect. Then we got the hint that this must be the solution because both equations are valid at this point. That was the idea. So this was the case, this was case one, and case two, we could plot the lines and then we see that they are parallel lines. Parallel means that in the Euclidean space, they're never going to intersect. So if they're never going to intersect, there is no way that there is a point in this 2D space that two equations hold at the same time, okay? Then we said there is no solution. So having a solution, a unique solution, that was intersection. No solution, parallel lines. And the last case was having an infinite number of solutions. Then this happens when we essentially have one equation because the second equation here is the same thing as the upper equation. It's just both sides of the equality are multiplied by 2, and that's not going to change the equation of the line. So they are intersecting at every single point in the space, and in some sense, one of the variables is going to be arbitrary. Whatever you choose, there is a solution. So in fact, we have 2 variables and we have 1 equation. We talked about minimum norm. Basically, that was when we had a wide matrix, if you remember, not enough equations for the number of variables. This led to the minimum norm solution. There are infinite possibilities. Find the one that has the minimum norm. We interpreted that as a minimum energy solution, for example, for a physical problem. So we started our motivation 100% for just solving a system of linear equations. We wanted to scale it up, arbitrary number of variables, to use a computer to solve it. So the generalization of that for n variables ended up being writing n lines of equations. So we realized that we can write this for any number of variables. It doesn't have to be 2, but of course, visualization was a problem. So we started looking more into algebraic and more abstract ideas for solving the system of equations and verifying whether there's a solution or not using algebraic tools. But this was not a good way of thinking about it. We needed to restructure many lines of equations into some objects that we can manipulate them easier and work with them in a more systematic way. And that led to the definition of vectors and matrices. So we learned that if we have n lines of equations in n variables with some coefficients, no matter what they are, those a coefficients, we can always write them in a matrix form for n by n, for n equations in n variables. That leads to a matrix of coefficients A, an m vector x that we stack our variables, and an n vector B, which is the right-hand side of this equation. So AX equals B. So we learned, you practice, you had homework, you give you equations, write it in a matrix form. Then we learned this compact notation, okay? Instead of many variables and lines of equations and coefficients, we don't really care maybe what they are. It's very difficult to look into individual terms. Now we are dealing with 3 objects, A, a matrix, X, a vector, B, a vector. This forms a general form of a linear system of equations for n variables and n equations. In other words, that's a square system of linear equations. Please feel free to ask questions if you want to maybe discuss any part. Sometimes I might move fast. So we learned about possible ways that attempting to solve a system of linear equations can basically turn out to be. We learned new objects, matrices, arrays of numbers, vectors. After that, we started thinking about more special matrices. What are the interesting cases that we might see in matrices? Purely motivated by applications and the utility they have in practice, some of them are very famous. One of them is a lower triangular matrix. A lower triangular matrix had this form that, if you remember, we call this diagonal. This was main diagonal or diagonal of our matrix. So all terms above the diagonal are 0. These matrices, we call them lower triangular. What was interesting about lower triangular matrices, what was it? Yes. So it was interesting because we could, you want to say it again? It's important enough, say it. Yes, the determinant as well. I don't have a slide for that. Good for bringing it up. We learned something called determinant. Determinant of triangular matrices was just the product of the diagonal. That was also interesting about them. But in the context of solving a linear system of equations, the structure of triangular matrices is interesting because if it's lower triangular, it leads to forward substitution algorithm. That means that if A is lower triangular, I give you a system of linear equations, you can solve it. You can code it, you can solve it, any number of equations. For example, here we have 3. You start from x1. x1 is 6 divided by 3. By the time you're in line 2, you know x1, then you solve for x2. By the time you're in the third line, you know x1 and x2, you solve for x3. So this turned out to be very important because we have an algorithmic way that scales up to arbitrary number of variables, and we can solve the linear system of equations. That's why triangular matrices are important. Then a natural way was to also talk about upper triangular matrices. And now you know that upper triangular matrices are, if A is upper triangular, now you know that A transpose is lower triangular. And transpose was take every row, put it in a column. First row becomes the first column of the new matrix, A transpose. Second row becomes the second column, and so on. So the upper triangular matrix has this property that everything below the diagonal is 0, the opposite of lower triangular. Now, in a similar context, and the upper triangular matrices lead to an algorithm that's called back substitution, back-forward substitution or back substitution. Now, instead of starting from the first row, moving forward, now we can start from the last row. Here we solve for x3. We know x3, we solve for x2. Then we know x3 and x2, we solve for x1. Again, this will scale up to an arbitrary number of variables. You can program it. You program this in Julia. You can have an algorithm for forward substitution. You can have an algorithm for backward substitution. If I give you a system of linear equations of any size, you can solve for that. Is that true always? You never faced any problem? Never? Right, so this was all good, and backward forward substitution were really fundamental to solving the linear system of equations, but we did set a condition that, well, we don't want any zeros on the diagonal, because then we're going to face division by 0, right? In the general algorithm, because each time we need to divide by this coefficient, right? If that's 0, we're in trouble. We cannot basically find that variable because we face division by 0. So assuming there's no zeros on the diagonal, this algorithm always works. So we spent a lot of time to deal with corner cases, right? So what happens is a 0, what happens, we have some special cases that it violates the ideal case of solving the equations. We talked a lot in detail about those cases. So we could do all of that without actually talking about matrix multiplication. You never needed to multiply matrices. You could have, you learned how to solve a triangular system of equations without even knowing what is a matrix multiplication. So matrix multiplication came into the basically our attention. First of all, if you want to go from the matrix form into the lines that we had, right, you need to multiply A by X in the sense of matrix times vector multiplication. That will give you each line of the equation. Now, we didn't need to go backward like that, but if you want to get those lines, that's what we should do. But moving forward, we needed that because then we're going to talk about factorization that involves multiple matrices are being multiplied and so on. So standard matrix multiplication was the first thing we covered. And that's generally what people think about when you tell them about matrix multiplication. Everybody thinks about this method usually. And it works this way, that for every entry ij, you take the ith, should call this maybe C. This is a new matrix C. You take the ith row of A, right, and multiply it by jth column of B. For example, we have here, what do we have? It's the second row of A multiplied element-wise by the first column of B, and then summing over that. And now you know that this is basically a dot product, right? You know now that if I have a row vector A1, A2, I have a column vector B, B2, I'm going to multiply them. You can write them as right? I'm dropping indices because for matrices we have to track more indices. But if these are just two vectors, this was basically nothing but the dot product of two vectors. So each row of a matrix is a vector. Each column of a matrix is also a vector. They are row vectors and column vectors. So every entry of a standard matrix multiplication is the dot product of a corresponding row and column. Rows are coming from the first matrix, and columns are coming from the second matrix here, B. We also learned that we verified it in different ways that matrix multiplication is non-commutative. You cannot just change orders when you're multiplying matrices. This is, in general, not true. You can pick two matrices, try it. Most of the time, it doesn't work. There are maybe special cases it works. But in general, this is not true. So dot product came a lot later in the lecture, but now if you go back and look at matrix multiplication, in general, you recognize dot products for each of the entries of C. So we can calculate a lot of dot products even in parallel for each entries, and that will give us C, okay? Now this was the standard case, but to come up with a new way to talk about factorization that is less painful in a sense. It's more intuitive. We decided to frame everything around the second way of multiplying matrices. A less known way of multiplying matrices is, in general, you have A n by k, B is k by m. It works this way that you grab the first column of the first matrix A, multiplied by the first row of the second matrix B. That gives you a matrix because you're multiplying a column vector by a row vector. This is going to be n by 1, right? A row multiplied by 1 by m. The result will be an n by m matrix, which is the exact same size of C if A is n by k, B is k by m. First column, first row, plus second column times second row. We keep doing this, right? Because we know that the number of columns of A is the same as the number of rows of B. Both are k. This way, matrix multiplication is defined, and we can do it. This interesting way of multiplying matrices, it's unusual, but it results in exact same output as the previous case. It is equivalent of that. You can show it by direct calculation and other ways. Second row times. So previously, we take the first row and multiply dot product with every column, right? Here it's just once. First column, first row. Second column, second row. All the way so we sum up k matrices of size n by m. This results in A times B. Looks interesting. But why it's useful? Because then LU factorization just came out of this naturally. And the way it worked, we're going to see it soon. So the second way of multiplying matrices was key to LU factorization. We used it as inspiration how we can basically layer by layer look into a matrix and factorize it into a lower and upper triangular matrices. An example here, 2 by 2 matrices, right? I'm not talking about partitioning, but by now you know that we can partition matrices into columns and rows. Then you take the first column times first row of B, right? Plus second column of A times the second row of B. This gives you A times B. Now, this was interesting to learn, but not because you're going to do matrix multiplication by hand like this, because you can multiply matrices in Julia anyway. You might not care what's going on deep down. Whatever is faster and in parallel maybe, that's good enough for you. This was motivation for LU factorization. Why did we need LU? Do you remember that? So everything is about solving linear system of equations. The story is, again, we have a system of linear equations, we want to solve it, there are 3 cases. Somebody told us that if it's lower triangular, you get forward substitution. If it's upper triangular, you get back substitution. That's wonderful. Then our question is, well, how the hell I get L and U? You need a new algorithm, right? So somebody needed to invent LU factorization so that people can use forward and back substitution. Then everything would be great. If somebody gives you LU factorization as a linear algebra library, right, then life is good. Probably the same person can implement forward and back for substitution for you too. Then we have a scalable tool for people who solve linear system of equations, and that's wonderful. But we need to understand where LU comes from. So LU was motivated this way. We said that, well, suppose I can write my matrix in a way that it's following the second way of multiplying matrices, C, right? Some column times some row, plus another column times row, plus another column times row, for a 3 by 3 matrix, right? You can always write this in this way, because you can stack the columns. This will be a matrix. You can also stack rows, and that will be another here, let's say 3 by 3, 3 by 3 matrix. So we recognize that the second way has this particular structure. Then we came up with an idea. If you remember, we came with an idea that grab the first column, divide by the pivot, the first element on the diagonal at the current step, right? Then multiply that by the first row, then subtract it from the original matrix to reverse, right, this process. The reversing process was grab a column, normalize it by the pivot, the element of the diagonal, multiply by the row, subtract it. That would zero out the corresponding row and column. We call that peeling the onion because you go layer by layer, zero out the first row and column. There you go. There you go. You got C1 and R1. Then we could repeat that for the second column divided by the second diagonal and the second row, right? You get C2 and R2. Because we are zeroing out at every step, then we observe that stacking columns leads to a lower triangular matrix, and stacking rows leads to an upper triangular matrix, purely because of this peeling the onion process, because we zero out rows and columns as we move forward. We don't leave anything behind. They're all zeroed out. So that this sum here holds in the end. So LU was basically a reverse, it's a opposite of this multiplication would give us L and U. So we've seen you during your homework. There is no such a thing as no tears in the math course. You all know that progress is incremental. I'm not going to claim that this was painless. It was a little painful, but you should have seen people before you. Go around on campus and ask graduate students, namely Trippy, your GSI. She might still have the mask somewhere. Now, you had to learn a bunch of other crazy stuff, like elementary matrices and a lot of other things to do LU. So this is a more intuitive way to do it. So I think we reduced the pain. We're proud of that. But of course, it's still challenging. You need to solve problems and examples to get used to it. So in an attempt to, by the way, peeling the onion, probably you should demand from Robotics to print a T-shirt for you. This idea came up last week. You should have a Rob 101 T-shirt with peeling the onion idea on it. Spread the word on campus. I would wear that. There's a GIF on chat as well. So LU factorization, we could construct it now. So any matrix A, first we said rectangular, square matrix, but later we also generalized the algorithm in the book as an optional read. You can also apply to rectangular matrices. So any matrix A, we can factorize it to L and U. Now, what is the systematic way to solve the system of equations without writing line by line and talking about each coefficient? So we start from A, x equals B. We know A is LU. Then we said, this sounds like a two-step process. If I define a vector y to be u times x, right? I just define this as a vector because u is a matrix, x is a vector. If you multiply them, it's going to give you another vector. Let's call it y. We don't know what it is. Then I can write this line as Ly equals b. Well, then I can solve for y, because now I can use forward substitution. I do forward substitution first to solve for y. Now, if I know y, then this line here that I'm showing it in the standard case when you see white in the right-hand side, if I know y and x is the only variable, I also know how to solve this, because then I can do back substitution to get x. So if you can factorize a to LU with two-step process, you can find x. Yes?
So in a case where we would have to solve Rayleigh factorization, we would be given L and U, or at the very least it would be given an algorithm to break it down into L and U, or we would be peeling the onion together.
The idea is that you're given A and B, right? And then you can factorize A to L and U and then solve this. Now you can do that by hand for small problems, but generally speaking, we want to do it by computer, right? You can use Julia's LU factorization. Of course, we had to send you through some homeworks to make sure you can get engaged with the steps of the process, right? And the reason that's important is not to annoy you, because to know the corner cases, the special cases that we face, you need to know the process, and then we can follow why is that something can go wrong. So we can link more advanced tools, the pro tips that we give you, to the reasons why they work. But the hope is that throughout your career, you don't use hand calculation. Now, one problem now we give you an example to do the LU, you continue, and then there is a 0 on the diagonal at some step, right? You saw that case, the pivot can become 0. Basically, maybe at step 2, right? You've done the first part. At step 2, the second element of the diagonal, what if this is 0, right? That means you cannot normalize the column. That was a problem. We recognized that when we saw it. So we could handle this like with different tricks, but the general solution for that is permutation matrix. So using permutation matrices, what we do, we swap rows. So it turns out if you just swap these two rows, it doesn't matter what line of equations is second, right? Because we can move it to the third when we write them in lines. When you have A1, 1x1 plus A2, 2x2 equals B1. And then you have a second line. Now, does it matter which line I write first? It doesn't matter, right? I could write the bottom line on top. That's not going to change anything. So permutation matrices are tools that allows us to swap rows equations when we work with matrices, because now we are working with new type of objects. Matrices is not like this, plus that's the way we can store it and work with it in computers. Permutation matrices can help us to swap rows. So the general algorithm for LU was that every time, a good way to, not necessarily the most computationally efficient way, but a stable way of doing it in the book is that each time when you want to process a column and row, do a permutation and bring the largest pivot on the diagonal to top, to the on that column, right? To be swap rows so that the largest value in that column is your current pivot. If you do that every time, you end up with a permutation matrix in the end such that P times A equals LU, right? Because if you swap rows of A, then you're not going to get the same L, right? Obviously, you're changing the columns and rows that you're getting from the algorithm. So AX equals B. Now we know that if you permute exchange equations, right, ultimately that will give us LU. But because AX equals B, we need to construct P times A on one side, we need to multiply both sides by P, permutation matrix. So we have to permute the right-hand side as well. Then we know that P times A is LU. So all it's changed is that the right-hand side needs to be multiplied by that permutation matrix. Then the same process works, right? So there's not a big difference in the way we solve the equations. The previous steps are valid. We just permute the right-hand side as well. Now, this LU with row permutation always exists. No matter what, for any matrix, you can do it. You can do column permutation as well. You can put the permutation matrix on the right side of A. But that's not necessary. That's just a choice that you might want to do that. LU with row permutation always exists for any matrix. So that was interesting. Of course, you could get 0 on the diagonal of U, but you could still perform LU. So I'm fast forwarding a lot. We talked about different cases. You get 0 on diagonal of U. We talked about linear independence. And all of that led to a protip, right? For a rectangular system of equations, AX equals B, and by M, a tall matrix. Ultimately, we said that, well, if the columns of A are linearly independent, that means we cannot construct any column from a linear combination of other columns. Then we could say that the determinant of A transpose times A is when it's not 0, then there's a solution, right? Now, if there's a solution, then it's unique. That was the condition to say that if there's a solution, then the solution is unique. Now, this was not for some advanced reason that we're not covering. This is not enough to LU, standard LU, is not enough to talk about which of the columns, right, are linearly dependent. We wanted to exactly pull those vectors from the columns of A. That led to the Uber protip. So this is something that you want to remember, because with this, you can look at columns of L and D. D is a diagonal matrix, and say exactly what column of A is linearly dependent. That sounds like a more specific tool, because one thing is that to know that the columns are not linearly independent. There's another thing to say that which column is linearly dependent, right? So this is more powerful. We call it Uber protip. It was as a result of a symmetric LU factorization. Because A transpose A is symmetric, and a symmetric matrix was such that its transpose is equal to itself. And then we know that A times B transpose gives us B transpose A transpose. So P A transpose A P transpose gives us LDLT factorization. L times D times L transpose. You could think of this as U, right? Because L transpose, you know, is upper triangular. So it is the same thing as LU, but this is a symmetric version of that. Then we say that if there is no non-zero, right, entry on the diagonal of D, then the columns of A are linearly independent. If there is a 0, the corresponding column from L is related to the column of A that you want to single out. That's the dependent column. Now, you need to be careful for the permutation, right? Because you're permuting A, so you need to basically map the permutation from L to corresponding column of A. But that's not very difficult because you have the exact mapping from exchanged rows in the permutation matrix. So the Uber pro tip was to check whether the columns of A are linearly independent and which of them are linearly dependent if there is a 0 on the diagonal of D. As you can see, this is a lot to take in. This was the result of a lot of lectures. I can freely put it on one slide here, but we spent hours and hours to reach to this point. Okay, just a remark. In the version that is implemented in the book, the way it's done, the algorithm, all the zeros are being, because we bring the largest pivot, right, to the current step, all the zeros are in the end. So if you do A P transpose, this will give you the corresponding columns, right? The columns of A P transpose will match the columns of L. Again, if you do it in Julia, you need to check how the algorithm works, but ultimately, if you have the permutation matrix, regardless of that, you can recover it. So you can look into A times P transpose. You can see that this is not something every time you want to think about, right? You maybe check one time, this is true in general, then every time you just want to multiply two matrices to find out the result. Okay, so then we reach to an interesting problem that happens in reality, because what if there is no exact solution, which at this point you knew that B must be a linear combination of the columns of A, then we would say that, well, there is a solution, because I've covered it at the end again, because now you know B is in the column space of A or range of A. Now, sometimes B is not in range of A, but we want to find a minimum error solution, least squares solution. The least squares problem for A being a tall matrix was this problem. I have a linear system of equations A, x equals B. There is no exact solution, but the columns of A are linearly independent. So A transpose times A is invertible. Because it's a square matrix, we can talk about the inverse. Inverse was only defined for square matrices. Now, the solution of least squares problem would give us the normal equations. Extremely important equation. This is one of those equations you can put it on the cover of the book. It's super famous and important enough. And people love it enough that you can put it on the cover, T-shirt, or whatever. This is called the normal equations. So both sides are multiplied by A transpose. And we know A transpose is invertible. So in fact, we can solve for X, right? But for large problems, we don't invert the matrix directly. But if it's a small problem, you can do that. So actually, this gives us a way to solve for the minimum error solution, least squared solution. So this is not the solution, right? Why this is not the solution? You're saying because we have more rows than columns.
Yeah.
That is partially true, right? Because that's the consequence of that. We need to satisfy more equations. But the concise, precise reason is that the solution means that this must be exactly 0. If it's a least square solution, it's not going to be exactly 0. However, this does make least square solution does make normal equations to be 0. So the solution of the least squares problem, this is interesting that it does solve the normal equations, but it is not the solution of the original equations, right? The solution you must get exactly 0. That's why this is the least squared solution to our problem. Emerald is asking about mean and argmean. It is a good question. Let me clear this. And we're going to talk about this in our future lectures too when we talk about optimization. And you need to learn it. It's a notation, so somebody has to explain it first. So if I have a function such as f, right? I can call this my objective function. When I say min, I mean minimize this objective function over variable x. Or you can write minimize. So this means find the minimum value that f of x can obtain over all valid, basically, numbers that can x obtain. However, when I say argmin f of x over x, now I mean that minimize f, but give me the x that f was minimum, right? Then this gives you the argument of f, my function x. So argmin gives you the x, but min, this just gives you the minimum value of f. Okay, so now we might use both you see in books and different literature. Not everybody is going to follow, precise definition, whatever way they learned. But the precise way of talking about it is that argmin means get x, min, minimum of f, not x. And when we write it this way, this is basically we are defining an optimization problem. Now, a particular objective function here is normed squared for our least square problem, right? This is a particular objective function that we choose. We call it least squares problem. Because we calculate the error, we find the norm, the magnitude of the error, and then we square it. And then we attempt to minimize it. Traditionally, this is the way people try to solve it. Because if you want to use calculus, this is nice. Because it's squared, you can differentiate it, and so on. But it doesn't have to be squared. But anyway, this is the least squares problem. I hope that was clear. And no, this is not a direct Julia command. This is how we define a problem, right? No, there are higher level languages that try to make it easy for you to define your problem. But this is not a command that argmin. There's a little more into that.
So for a least square solution would be that x star?
Yes, x star in this case is the least square solution. Again, a times a star minus b won't be 0. However, a transpose a times x star minus a transpose b will be 0, right? Now, as a special case, when the system is square, right, and all columns are linearly independent, this does give you the exact solution. But that's a very special case. In practice, in engineering, that's usually never the case. It's always a good thing when your algorithm reduces to the nominal case. It gives you the expected result. So we will talk about more about optimization in future lectures in the course. You will have the opportunity to ask more questions. So we continued a lot on vector spaces. We started working with Rn, set of all n vectors, such that every entry is a real number. This was our vector space, Rn. And then the property of vector spaces was that the linear combination was defined in a way that alpha times x plus beta times y. Alpha and beta are real numbers. X and y are vectors. This notation means in or belong. That means x and y belong to or live in the space Rn. So you can multiply a scalar by vector, and then the scalar gets multiplied by each of the entries. And then you can also add them. The rule of vector addition is the same thing also for matrices, is that you just add corresponding entries. The first one with the first one, second with the second, and so on. For matrices, you just follow the indices, right? The corresponding indices. The first row, second column should be added to the first row and second column of the other one. So if two matrices are not the same size, we cannot add them. It's just not defined. Then we wanted to talk about subspaces. Rn is huge. It's the huge space of every n vector that you can imagine. Is there any subspace, subset of that set that is special? Then that led to the notion of subspace. So imagine you, instead of the entire space Rn, what if you're talking about It's a smaller subset of that, a portion of that. Non-empty, of course. Then a subspace was even more special than subset in the sense that if you choose any two vectors v1 and v2 and get their linear combination, you remain in that set. Pick a subset, pick two arbitrary vectors from that subset, calculate their linear combinations. If it still belongs to that subset, then your subset is a subspace. So not every subset is a subspace, right? But every subspace is a subset. You could say that. Then we learned a tool. How do you generate subspaces, right? Sounds like a very special subset. How can we generate them? Is there a way? We know how to check them. We check linear combination, if it's in the set or not. The span was the tool that enabled us to generate subspaces. I could give you a set of vectors, right? And then you could create a larger set by including every possible linear combination of those vectors. And that would be the span of that set. So S is a set of vectors, the set of all possible linear combinations of its elements give you the span of S. And the span of S, by definition, is a subspace because it includes all the linear combinations. Whatever you choose, it is already contained. Now, the consequence of this linear combination is that it must include the zero vector, right? Because if the subspace is closed under linear combination, that means that the coefficients, alpha and beta, can be also zero. If you choose them to be zero, it gives you zero vector. So an easy way to check a set is a subspace or not is that quickly check if it contains the zero vector or not. If not, it is disqualified. It's not a subspace. If it is, then you can check for the linear combination. This is your life on fast forward now. These are vector spaces. Again, these are like a story of what we went through. See, which topic is still, it's not clear to you. It's a good way to find out where to focus. We spent a lot of time talking about vector spaces. We have 3 chapters. Each chapter, maybe we spend 2-3 lectures, right? I'm going to summarize all of that in 10 minutes. How much you will learn from today? Probably not much. It's more of a diagnostic tool. But it's a good way to see we've come a long way. You can talk about very advanced topics. These are very advanced topics that we use in practice. And don't worry, it's November, Christmas is around the corner. Semester is almost over. So we learned about a set of vectors, span. Then we learned a new technique called Gram-Schmidt process. The Gram-Schmidt, what was doing was to get a set of vectors that are linearly independent, make every pair of them to be orthogonal. Because when we learned dot product, we realized that if 2 vectors are orthogonal, right, their dot product is 0. So Gram-Schmidt process uses this notion to remove the overlapping part and generate a new set of vectors that are now orthogonal. So this was the motivation for orthogonalization is the motivation for using the Gram-Schmidt process. Now again, given the set of vectors that are linearly independent, because if they're not, you're going to end up with zeros somewhere. You give a new set of vectors, orthogonal, every two of them. If you take the dot product, it will be 0. It preserves the span. It will not change the span of the original set of vectors because you only remove the redundant part, overlapping directions from each vector. So each vector points to an independent direction in the space. Span is not changed. They remain linearly independent. Now, this was an interesting process that led to QR factorization. Out of Gram-Schmidt process, we got QR factorization. Because now, if you pick your orthogonal vectors and arrange them into a matrix Q as its column, with some more detail that there are some coefficients, arrange those coefficients into a matrix R that takes the upper triangular form. We talked about it. So purely out of the Gram-Schmidt process, we get, you can normalize them by the way too if you want. You get QR factorization. This is not the only algorithm to get QR. There are several other algorithms. In different contexts, some are preferred over the other ones. But a standard way of doing QR is to use the Gram-Schmidt process. So Q, an orthogonal matrix, orthonormal, more than orthogonal. They're also normalized, so you get the identity matrix. Has this property that Q transpose Q is the identity. And we can factorize any matrix A. A can be rectangular, tall, here. You get Q times R. R is m by m square invertible, and it's upper triangular. Q is n by m orthonormal. That means its columns are orthogonal and normalized. Normalization is when you divide the vector by its norm, so that the norm of the new vector here, E, will be 1. Orthogonal and normalized, then orthonormal. So we learned a new way of solving least squares, now using the new factorization. I give you AX equals B. A is QR. Multiply both sides by Q transpose. Because Q transpose times Q is the identity, I get Rx equals Q transpose B. So if I have the QR factorization, with one back substitution, you can find the solution. Another interesting fact here is that you do not need to form A transpose A. With QR factorization, you can directly work on A. Whereas LDLT, we had to form A transpose A. So the modified Gram-Schmidt, that is not the standard version, it avoids division, the stage that we get columns of Q, and it is numerically much more stable than LU because it avoids division. Dividing by numbers is always bad. You don't want to do that in your numerical algorithms. So this QR factorization is numerically more stable, and you can work directly on A. So you learned that, well, there are other ways to factorize a matrix, and there are other ways as well. You might come across them in the future, but these are the very famous ones that we talk about. There is a more general way of factorizing matrices called SVD. We are not covering it here. We might talk about it in the end, maybe. This is the only factorization that is better than QR. It's more general. But the beauty of LU and QR is that they're tightly integrated to the concepts that we want to learn. They naturally come out of our motivations for solving linear systems and having direction, basis in the space that are orthogonal, right? These simple notions lead to these factorization, then they are more interesting to learn in the beginning because of that. Another advanced concept that you learned was basis. We give you a set of vectors, right? The subspace. Set of linearly independent vectors, and then you get the span of them. You can make a subspace V. The maximum number of vectors that are linearly independent in this set that you have, it's dimension of this subspace, which is K here. And each of these vectors would form a basis for you. And we talked about coordinates. I'm not going to bother you again, but we learned about bases, and a special case was when we use canonical bases, the columns of the identity matrix, which for a simple example of, let's say, R2, canonical bases are these familiar orthogonal directions, right? In 3D, your IJK, they use in physics. These are the columns of the identity matrix. We call them canonical or natural bases. And the last topic that we covered in the previous lecture is now we want to start thinking about matrices as functions. Matrices are functions that takes a vector, acts on it. The action is when you multiply a matrix by a vector. The matrix A acts on the vector and then give you another vector, such as f of x, or you could call it y, right? F of x to just emphasize that this is a function of x. X can be anything. So it's a mapping from domain to range. If A is n by m, takes an m vector, gives you an n vector. The range of A, at most, is going to be Rn. But we learned that that's not always the case. Because, for example, for a 10-dimensional vector space, R10, right? Your matrix might have only 6 columns. Linearly independent, but it's not going to map to the entire space. There will be a subspace of that, right? That was the tricky concept because every column is basically a 10 vector, but it uses 6 spaces to cover a subspace. So that was possible for a matrix to happen. So the function view of matrix leads to two very important concepts, null space and range. So the null space, with all the motivation, we've seen it before, homogeneous set of system of equations and all of that, it led to this concept that take the set of all x values, Rm, such that when you multiply a by x, you get 0. That is the null space of A, and we proved that null space is a subspace. Because if you pick every arbitrary vectors from the null space and form the linear combination of them, you still get 0. So null space is a subspace. Now, if you only have x equals 0, this is always a solution of ax equals to 0, right? This is the trivial solution. So x equals 0 is the trivial solution. Your null space has at least always the 0 vector. But it's more interesting when it has more. What are those possible vectors that a times x gives you 0? Because then we could add it to any solution of the system. It wouldn't change it. You would get, going back all the way to 3 figures that I had, right? When the null space has any non-zero vector, you could get infinite number of solutions. Which now you started imagining that, well, there is something here parallel with what I'm trying to solve, right? That is not affecting my solution, but it can be anything. So go back and try to connect it to that line. Now, if that's the case, then it must be orthogonal to the set of solutions, right? And that's true. You can prove that null space is orthogonal to basically your solution. So the second one was range of A. So range of A is when you don't get 0, right? Because you can also get just another vector. So when you get 0, you get null space. When you don't get 0, whatever possible value you might get for y in Rn, that's the range of A. And at most can be Rn, but it can be a subspace of Rn. So range of A is nothing but the column span of A. Pick the columns of your matrix, right? The span of these columns, assuming, well, they don't have to be linearly independent because then the span will be basically smaller. So the span of your, the columns of A, or column span of A, is in fact equal to range of A. And eventually we summarized it that for a system of linear equations, n by m, A is a rectangular matrix. There is a solution if and only if B is in range of A, meaning it's a linear combination of the columns of A. If there is a solution, right, it is unique if the null space is it only contains a 0 vector, because otherwise you get infinite number of solutions. null space is a subspace. If there is such a vector in null space that is not 0, then every alpha times x bar is also in null space. So you get infinite number of solutions. So it is unique if the null space is only the 0 vector, contains only the 0 vector. In other words, if you have a vector, again, in the null space of A, so this is a solution, then the set of solution is x plus null space of A. Every vector in the null space can be added to that solution, and you get a valid solution. That's how we end up in general with an infinite number of solutions, right? Again, there are 3 cases. There is a solution, and it is unique. There is no solution, right? And there are infinite number of solutions. This is all go back to those 3 cases, 3 figures. So you can put them together that Ax equals B has a unique solution if and only if B is in range of A and the null space is the 0 vector. The Zoom ended. I think the recording ended. Here, that's okay. This is the same as the last lecture.